Greetings everyone, and welcome back to my channel. This is the third video of a series where you will explore a variety of concepts and ideas regarding differential calculus, as well as their practical uses in real-life contexts. Today's topic are the lines known as tangents and normals, more specifically, what they are and how to find them. At this point in time, I have mentioned tangents on multiple occasions, therefore you must be familiar with them, namely with what they are. Though, as a reminder, a tangent is a straight line that smoothly or barely intersects with a nonlinear function, or a curved line if you will, at one point. The point with which it intersects is the point of tangency. By definition, tangents are linear functions, and thus their equations are written as y equals mx plus c. Here is an example to visualize this idea of barely and smoothly touching the line at one point. It is clear that the straight red line converges with the blue parabola, then they meet at one point and begin to separate again. The point of tangency in this case is 6, 5. Being a straight line, the tangent must have a gradient, and in this case the gradient of the tangent is positive, as the y values on the line clearly increase when the x values also increase. M is greater than 0. However, the gradient may also be negative, and even 0, meaning the line is horizontal. Before continuing, I would like to discuss a small misconception people have about tangents. Some claim tangents intersect with a line at one point only. Unfortunately for them, however, that is not true, and there are many examples of tangents intersecting with lines at 2 points, or even more, such as here. This distinct tangent intersects smoothly at this red point, and then proceeds to cross the line again at the green one here. However, it does not intersect it smoothly, rather it simply crosses it. Though as a matter of fact, a tangent can intersect with a line smoothly at multiple points as well, like it is displayed in this graph here, where the tangent intersects with those 2 points at the bottom of the line. A tangent line may cross the other line multiple times. What makes a tangent is the fact that it intersects with the line smoothly at least once. Anyways, that was simply a recap of what you were already aware of. Now it is time to discover how to find these tangents. Assume we have the simple cubic function f of x equals x cubed. We will not need it, but here is a graph of the function in case you are curious. Our goal is to find a tangent to f of x at x equals 1. Effectively, we are looking for a tangent that would intersect the line of f of x at the point x equals 1. The first step in solving this is to remember one crucial fact. Tangents are linear functions. Thus, we may write their equations as y equals mx plus c. Once we have established that, we know that we must discover two variables in order to solve this problem, m and c. You may recall from my last video how I mentioned the following. The gradient of the tangent is equal to the gradient of the function at the point of tangency. Fundamentally, the gradient of the tangent will therefore be equal to the instantaneous rate of change. To find the instantaneous rate of change at any point on a function, we use its derivative. Therefore, we must use the derivative of our function f of x and find what result we get if we input the point we are looking for into the derivative. In our case, our gradient m is equal to f prime of 1. Using the power rule we have discussed last video, we can easily find the derivative of this cubic function, and we get that f prime of x is equal to 3x squared. The final step in finding the gradient is inputting the point we are looking for, in this case 1, in the derivative, as such. Our result is that m equals 3. Finding c, also known as the y-intercept, is a bit more complicated. If we once again look at the equation y equals mx plus c, we realize we know two things. We have our value for x, which is equal to 1, and we have our value for m, which is 3. We cannot find c yet, but we can find y. What we're going to try to do is to find the coordinates of the point of tangency at x equals 1 and make our straight line with a gradient of 3 go through it to get our y-intercepts. Oftentimes, you will have already been given the coordinates of the point of tangency. Here, however, we must find it ourselves. We have our x-coordinate already, which is equal to 1. And to find the y-coordinate, we must simply input the x-coordinate into the function f of x. Thus, y equals f of 1. We calculate what y is, and then we discover it is equal to 1. We input that knowledge into the equation above, and now we have enough to solve for c. We obtain c is equal to negative 2. Now that we know what the gradient and the y-intercept of the tangent are, we may finally write its equation, y equals 3x minus 2. If we want, we could now write a general formula for finding the gradient and y-intercept of a tangent for any point on a line. Assuming our point is x equals a, the formula for the gradient will be m equals f prime of a, while the formula for the y-intercept will be f of a minus f prime of a multiplied by a. We are done with tangents, and now I move on to the second half of this video, the normals. I have never mentioned these in my videos series before, as they are not as important as tangents. Nevertheless, it is still very much useful to know what they are and how to find them. In essence, a normal is a straight line perpendicular to a tangent, and which intersects the line at the same point as a tangent, that is, the point of tangency. For those unaware, perpendicular means there is a right angle, so a 90 degrees angle, between the two lines in question. Here is what it would appear like on a graph. The red line is the tangent, and we can see how the green line intersects with it and the blue line at the point of tangency, 2, 5. Additionally, you may notice how the red and green lines are perpendicular. The gradient of this normal is positive, while the one of the tangent is negative. It may be the other way around as well, with the normal having the negative gradient while the tangent has a positive one. That is always the case, in fact. Furthermore, if the gradient of the tangent is 0, the normal will have a gradient of infinity or undefined on calculators, and vice versa. At last, we must now learn how to find these normals. We shall say we have the function f of x equals x squared plus 2x minus 1, with its graph right below. The task is to find a normal to x equals negative 2, a normal that passes through that point on the parabola. Just like tangents, normals are linear functions, and their formula is written in the form y equals mx plus c. Yet again, we must find the gradient m and the y-intercept c. To find the gradient of a normal, you must recall one important fact. Gradients of perpendicular lines are negative reciprocals. In other words, if you multiply the gradients of two perpendicular lines, they will equal negative 1. Thus, the tangent's gradient multiplied by the normal's gradient will result in negative 1. We can rearrange the formula and get that the gradient of the normal equals negative 1 divided by the gradient of the tangent. Now, you may recall from earlier in the video how to find the gradient of the tangent. In fact, we've made a formula for it, which states as follows. The gradient equals f prime of a being negative 2 in this case. So, the gradient of the normal is negative 1 over f prime of negative 2. The derivative of this function is 2x plus 2. I found that using the power rule. We substitute negative 2 into the equation and get a negative 2 to be the gradient of the tangent. And finally, we divide negative 1 by that gradient to get the gradient of the normal, which seems to be 1 over 2. Finding the y-intercept of the normal is no different from finding the one of the tangent, hence why we should use our formula we made previously for finding it. There is one thing that must be adjusted, however. F prime of a is the gradient of the tangent we use to find the y-intercept of the tangent, but now we're trying to find the y-intercept of the normal, and therefore we should use the gradient of the normal. As a result, we replace the f prime of a with negative 1 over f prime of a, since that is the gradient of the normal. Additionally, we replace the minus minus with a plus to simplify it. A is negative 2, so now we simply find what f of negative 2 and f prime of negative 2 are to be able to find our y-intercept. F of negative 2 is negative 1 according to our calculations, and f prime of negative 2 is negative 2. Finally, we discovered the y-intercept to be 0. The final answer to this question is that the formula for the normal at x equals negative 2 is y equals 1 over 2x. Once again, I shall leave the formulas we have used to find the gradient and the y-intercept down below here. Now that I have finished explaining how to find the tangents and normals, it is time to test what you have learned with two exercises. To begin, you have the function f of x equals x to the power of 4 minus x to the power of 2. The task is to find the equation of a line tangent to it at point x equals 1. I urge you to pause the video now and solve it by yourself. Of course, if you need to, you may return to previous sections of the video to see how I solved such a problem. So, we must find the gradient and the y-intercept of that function using the previously explained methods. First, we will focus on the gradient. This is the formula we have created earlier, where a equals 1. In order to use it, we must find the derivative of the function f of x. In this case, f prime of x is equal to 4x to the power of 3 minus 2x. We now simply substitute 1 for x in the derivative to discover what the gradient m is, and it turns out m equals 2. We now repeat the same method but with the y-intercept. To use this formula we must find f of 1 and f prime of 1, so let us quickly do that. F of 1 is 0 and f prime of 1 is 2. Finally, we put these values into our formula to get the y-intercept. The answer is negative 2. The last step here would be to create the formula in the form y equals mx plus c, knowing m is 2 and c is negative 2. The final answer is y equals 2x minus 2. If we plot the function f of x and its tangent on the graph, we do in fact see how the red tangent barely touches the blue line at x equals 1. Finally, I present you with a very similar exercise. Here is a function, and you must find the normal at x equals negative 3. Do this by yourself before watching me do it, and once you are done, watch the rest of the video so you can check if your answer is correct. Good luck! Just as we did with the tangent earlier, we will search for the gradient first. Using this formula I presented previously and substituting negative 3 for a, it will yield us the gradient. The derivative for this function is 4x minus 5, and now I may solve the problem. According to our calculation, where we substituted 3 for x in the derivative and divided negative 1 by that result, we find that the gradient is negative 1 over 7. Next, we find the y-intercept using another formula I presented earlier. First, we will solve f of negative 3 and f prime of negative 3, which are equal to negative 3 and 7 respectively. At last, according to the calculations, c equals negative 24 over 7, meaning the formula for the normal is y equals negative 1 over 7x minus 24 over 7. This is confirmed by the graph here, in which it is clear how the red tangent and the green normal are perpendicular, as well as how both intersect with the blue line at x equals negative 3. This video seems to have come to an end, unfortunately. Nevertheless, I certainly hope my video has helped you understand what tangents and normals are and how to find them. Thank you very much for watching. If you enjoyed, leave a like and comment, and give me some feedback on the quality of my video and my teaching. Furthermore, if you have any additional questions, you may ask them in the comment section. Have a wonderful day and farewell.